Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. This channel provides basics of finite element analysis and computer-aided mechanical engineering design and analysis using CAD-related software. Let's get started.
Hello friends, today I'll show CFD conjugate heat transfer analysis and optimization using SolidWorks flow simulation. Let's see the model. This is the model. It is consisting of multiple numbers of pipes having diameter 20 mm, and top of this one we are having a rectangular plate which is acting as a heat source, right? It will be providing heat at a rate of 1000 joules per second, that is 1000 watt heat will be providing by this top plate, and from this small diameter pipe will be providing freon gas at a rate of 0.05 kg per second, and our goal will be to check the steady state temperature of the fluid as well as the solid also, right? Let's get started. The leads have already been provided at these ends. We're starting with flow simulation, and we have to create the environment of flow simulation through Wizard. We're considering this project as default name as project 6. Next, considering the unit as SI system, and we're taking temperature as degrees Celsius. Next, we're considering this one as an external analysis, and it will be heat conduction in solids. At the same time, gravity will be required. As top plate is heated, hot air will go off. We're considering gases will be air particles. At the same time, we want to take freon gases as a coolant. We want to take freon R123. Next, solids we are taking aluminum as solids. Next, default roughness we are considering. Next, we will consider the concentrations. Initially, inside these pipes it will be only refrigerant, so it will not be a mixture of air and refrigerant. So inside this pipe the concentration of air will be 0 and it will be filled up with refrigerant, so its concentration will be 100%. This 1 it will be finished. Now we can see the computational domain. Okay, now thing is, the computational domain is very big, very large. Our task should be to reduce this computational domain. If you reduce this domain, the calculation time will be little less. So we're reducing this domain. It appears to be okay. Computational domain is ready. We're making this domain hidden. Next one, what we have to do, we have to create a heat source at the top of this plate. So we're starting from tools, flow simulation, insert, surface source. This one will be working as a heat source. It will be providing heat at a rate of 1000 joules per second or 1000 watt. Next one, we have to see the fluid subdomains. We can do one thing. Before selection, we can make all these parts transparent. That will be better. So we should go back to the model again. Select the model, selecting the parts completely, change transparency. Now it is transparent, right? Make the top plate also transparent. You can see the model completely transparent. For proper selection, we can make that object segmented. We can make it completely half. Then selection will be better one. You can cut it from top plane, and we can make it move little downwards, in which you can select the pipes properly, right? These are the pipes. Now we have to select that fluid subdomains. Insert fluid subdomain. It will be only freon passing through these pipes at a temperature of minus 10 degrees centigrade. So the path to be selected, this is the fluid subdomain, right? Done. We will apply boundary conditions. Insert boundary condition. Initially, through these pipes, we have to provide freon at a rate of 0.005 kg per second. And its temperature will be minus 10 degrees centigrade. So we are coming to the temperature from thermodynamic parameters. Its temperature will be minus 10 degrees centigrade. And substance concentration, it will be 100% freon. So freon 1 and air is 0. It will provide the location, right? We are providing from here itself. Mass flow rate at 0.005 kg per second. Then check. Done. Now another boundary condition to be provided at the other end of this pipe. So boundary conditions, insert boundary condition. You have to apply atmospheric pressure at the other end. So static pressure and temperature is normal temperature 20 degrees centigrade at the other end. Select that end properly. Done. Green check. Boundary conditions have been applied properly, so we can see the complete body again. This is our complete body. Boundary conditions have been applied properly. Now we can provide some goals, right? As I told earlier, that our goal will be to see the steady state condition, temperature of fluid and solid also, right? So we'll select some goals. Insert global goals. We want to see temperature of fluid, maximum temperature of fluid, by the same time maximum temperature of solid also. As our goal to see the steady state condition, so at a steady state condition both will be having same temperature. Okay, go and check. Another thing, we can see the temperature at the exit end, right? That will be surface goals. Insert surface goals. We will see maximum temperature of fluid at the surface. Select other, number 1, green check. Another thing we want to see the temperature at the top plate. So another surface goal we want. Surface goals, maximum temperature over the surface, right? Green check. Now we can run it. While running, you can see the solver window. We'll see the results when it finishes. Still meshing is going on, then it will start iterations. The solver is finished, so we can see the results right now. First result we'll see from cut plots. Insert cut plots. We can see the results. With respect to top plane will be better one. So let's select the top plane. With respect to top plane, we want to see better will be if we see from front side. Can select the plane properly. Can move it little bit down. So from the mid of this fluid particles we can see. Okay, done. This is showing pressure. We're going to see fluid temperature. You can see the temperature is starting from here, minus 10 degrees centigrade, and finally it has come to 129 degrees centigrade. Right? This one we can see in the form of one animation also. Let's see the cut plot in form of animation. Play. We can view the cut plot from other planes. Cut plot, clear and hide. Cut plot 1, edit definition. We'll see this one with respect to some other planes. Let's select the right plane and want to move this right plane. Let's view this one from one side. So we'll move this one along middle of any fluid profile. Let's see this one along this way. We can see one animation also. It will show the temperature profile along its path. Let's clear and hide this part. Surface plots, insert surface plots. We'll see temperature of the solids. So we'll select that top surface and it will be temperature of solids. You can see the temperature at this place is very high, 129.8 degrees centigrade, and here it is in the yellow range, that is in the range of 113 to 118 degrees centigrade. As we have provided cooling from these pipes, it started from here. So throughout this path, initially the temperature of the plate was less, and at this side, as it is moving from right to left, its temperature is increasing. Right? At the same time, you can see the temperature of fluid also. This is the pattern of temperature of fluid. So it is almost throughout the same. It is 129.82 degrees centigrade. Right? Now we'll do another thing. What you see throughout this whole body. So surface plot 1, clear and hide. Another surface plot we want for the whole body. Insert surface plot. You see all faces. It is showing the temperature of fluid, by the same time temperature of solid also. You can see throughout this passage, initially here the temperature of fluid was a little bit less, and throughout this passage it has suffered some kind of conduction also, as it is connected with this one. So heat has been transferred from this top plate to this fluid. Right? These are the things we can see. Now next one, we have to go to the particles flow. We can see it from flow trajectories. Surface plot will clear and hide this part. Next one, we will show flow trajectories. insert, we will see in the form of arrows only, and temperature of fluid, we can see velocity also. Let's see velocity of fluid. It will passing through these pipes, so select other, lead number 2. Okay, you can see how the freon particles are moving throughout these pipes. You can see throughout this passage of, these are the coolant freon particles moving from inlet to the exitant. By this color change, you can see how the velocity is changing. Initially the velocity was in the range of below 0.39 meter per second, and throughout this passage, while it is passing at the exitant, its velocity is high in the range of 3.5 meter per second. Right? Temperature of fluid, we can check. Through this color you can see initial temperature was in the range of minus 10 degrees centigrade, and while passing through these pipes, its temperature increased in the range of near about 101 degrees centigrade. You can see the color is yellow, so it is in the range of 101 degrees centigrade. Okay, right. Now we want to see our goals. Right, let's clear and hide this part. Flow trajectories, clear and hide. We're going to see the goals, goal plots, insert all goal plots, show. It is showing that maximum temperature of fluid equal to 129.82 degrees centigrade. That means it is the steady state temperature. At the same time, the maximum temperature of solid also 129.82. That means steady state condition is achieved. Both are having similar temperature, right? And we have seen the maximum temperature of fluid 1 equal to 109 degrees centigrade, and maximum temperature of solid equal to 129.82, and fluid temperature is equal to, at the exitant, at the exit surface, fluid temperature equal to 109.46 degrees centigrade, right? And maximum temperature of fluid equal to 129. Okay, these are things we can see in the form of graphs. Next one, we want to go for optimization. That means we have seen that maximum temperature of fluid equal to 129 degrees centigrade, right? So we have to optimize such a way that we want to reduce the temperature of fluid. Maximum temperature of fluid should be, let's say the maximum temperature of fluid we want to be 100 degrees centigrade. So to reduce the temperature of fluid, we want beta cooling, right? So beta cooling means you have to provide more mass flow rate. By the same time, you can do one thing, we can increase the diameter of these pipes, right? So let's see how we can optimize these things. We start optimization from solve, new parametric study, and while doing parametric study, we want to do a specific type of like goal optimization. For goal optimization, we can do a lot of things, like we can provide some input variables from the boundary conditions, or we can provide some dimensions also, right? Here in this case, we feel that input variables will be better one for optimizations. We want to reduce the temperature of maximum temperature of fluid from 129 degrees centigrade to 100 degrees centigrade. So for reduction of temperature for this freon, we want to provide more cooling with more mass flow rate, right? So we're considering these variables from here. The variables are maybe in the form of heat source or boundary conditions. Heat source we are keeping constant, and boundary conditions we are considering variables. We are taking mass flow rate to be variable. Mass flow rate we are considering little higher. Okay, initial mass flow rate was 0.005 kg per second. Now we want to change this mass flow rate from 0.006 to 0.6 kg per second. This is the range. Now with this range we have to see the criteria, and criteria is dependent on goal. Our goal will be to have a maximum temperature of fluid to be 100 degrees centigrade. We are selecting a lot of goals, but only here in this case you want only one goal to be optimized. You want maximum temperature of fluid to be 100 degrees centigrade. Okay, so that target value should be 100 degrees centigrade. And we want a deviation in the range of plus minus 0.1 degree centigrade. Let's see the scenarios. Our target is to have a maximum temperature of fluid to be 100 degrees centigrade. For that, what will be the inlet mass flow rate, that to be finalized here itself. Okay, let's run it. While running, with maximum value of mass flow rate, it will calculate the temperature of fluid. When it is finished, then it will go with the minimum minimum mass flow rate. In this way it will try to narrow this range, and finally it will find out the optimum. Let these iterations and calculations go on. When it finishes, we'll see the result. Let these calculations go on. All the iterations have been finished. You can see that 8 numbers of iterations have taken place, and you can see the solution is converged. That means our goal is achieved. We'll see the results. We're told that at 0.05 kg per second mass flow rate and coolant temperature minus 10 degrees centigrade, the maximum temperature of the coolant with this conduction effect was 129 degrees centigrade. Now by keeping the heat source same, we have changed the mass flow rate of coolant from 0.6 to 0.006 kg per second in the range, and with a value of 0.007635778182 mass flow rate kg per second, we got the temperature of fluid equal to 99.97 degrees centigrade. So we got our results, optimized results, after 8 numbers of iterations, right? Like the same way you can optimize a lot of other things by varying different input variables. The input variables may be the dimensions of this pipe. Maybe you can increase the diameter or decrease the diameter. By the same time, you can increase the length or increase the heat source temperature also, right? This is all about today's conjugate heat transfer analysis and optimization. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.